Good day. Today we are going to learn more about the electric field. We already have several ideas about the electric field, but now we will try to quantify it, putting a number to the electric field strength so we can really have a mathematical description. And mathematical descriptions are great because they are accurate and precise. But before that, let's clarify the difference between force and field. Force is an interaction between two objects, and the field is a manifested or sourced by one object. So you remember from Coulomb's law that in order for a force to exist, two objects must have charge. So in this case, the force is attractive. There's a force on object 1 due to object 2, and a force on object 2 due to object 1. In any case, forces always comes in pairs. It always involves two objects. Now, a field is manifested or sourced by just one object. You don't need two objects to create a field. To manifest a field, you only need one. In this case, it's just one positive charge, and it's producing an electric field that we can visualize to be radially outward. Okay? You need one charged object for a field. You need two charged objects for a force. Now this is a negative charge, and we know that for negative charges, the electric field is pointing radially inward. It's really hard to draw. Okay. And what else do we know about this? We know that the electric field is strongest close to the source. So here, at this point, let's call this point A. And here we have another point, point B. And here we have another point, point C. Which point has the strongest electric field due to this charge? It's point A. The electric field here at point A is strongest, and point C is weakest because it's farthest away. Now that's well and good, but numbers are better at becoming more precise with your description of electric field strength. We have just described electric field strength as strongest, stronger, and weakest, but we need numbers. For example, we can assign for letter A a number for the electric field strength to be 100. And maybe for B we can assign 70. And for C we assign 20. C isn't numbers better? Because now we can see that to what extent B is lesser than A or C is lesser than A. We now have a number. And it turns out that for electric field, we do have that number called electric field strength, and we actually even have units for that, newtons per coulomb. These are electric field strengths. Okay? So newtons per coulomb is the unit for electric field strength. We will learn more about that later. So the electric field is said to exist in the space near a charged object. The charge that causes the field is the source charge. Why is it called the source? Because it is the source of the electric field. But to measure the electric field, we place a small test charge in the field. So there's a difference between a source charge and a test charge. Okay. Putting test charge in space to measure the electric field. These are just three dots, three blue dots. They are not charges. They are not charged objects. These are three dots in space. So what we want to do is we want to put a test charge on each of those dots to try to measure if there is any electric field. So let's say, for example, we put a red test charge here, call it Q. Then we observe it, okay? What happens to Q? Oh wow, it experiences a force. Oh. Well, let's say our test charge is 1 nanocoulomb. Let's make it very small. Nano is 10 to the negative 9. And the force is, let's say it's 10 newtons. Wow. Why don't we get this test charge and place it here? It's the same test charge, 1 nanocoulomb. We notice that the direction of the force is different, and it's much weaker. 8 newtons. How about we put a test charge here? It's a really weak force. It's the same Q1 nanocoulomb, but the force is pointing in a different direction, and the force is maybe a lot weaker, 2 newtons. So now, do you have an idea where that source of the electric field might be based on the arrows and the directions of the arrows? Well, somewhere here. We didn't know that it's there, but when we put test charges, we realized there must be some charge somewhere that's causing this electric field. And true enough, there it is. Now, I draw this concentric circle just to illustrate that around that circle, around the perimeter of that circle, you will always get a force of 10 newtons for every charge of 1 nanocoulomb that you place there. So this concentric circle, it's imaginary, but just to illustrate that wherever you put that charge around that circle, it will always experience a 10 Newton force with varying directions, but always 10 Newtons force. Same is true here. Wherever you put that charge, the 1 nanocoulomb, around the circumference of that bigger circle, you will always get 8 newtons. And it's smaller because it's farther apart. The force is smaller because it's farther away from the source. And the same is true for the farthest point. Okay. So the force per charge ratio. Electric field strength is equal to force per charge. Here, this charge is the test charge. Sorry, I just can't find the cursor, so and this force here refers to the force experienced by the test charge. So what is this formula all about? By test, really hard to type or to write. In order to determine if there is an electric field strength in any point in space, you can do so, you can find that electric field by putting a test charge at that point and noticing if there are any effects to that test charge if it feels a force. So there's something very important here. The electric field will always be there even if you don't put a test charge. Okay? Just like the wind will always be there even if there is nothing to blow on it. But we put the test charge there, it will not influence, the test charge will not change the electric field. It will only be there to discover that it exists. Okay? And we know that the electric field exists because that test charge experiences a force. So it's really important that I'm going to stress it again. The test charge does not affect the electric field. The electric field is not affected by the test charge. The test charge is only there to measure the electric field. The electric field will exists even if you don't put a test charge there. Okay? And there's another charge somewhere that is producing that electric field. But this is another very important formula. So that previous formula, E equals F over Q, where Q is our test charge. E is not directly inversely proportional to Q, no. And E is not a function of Q. This, as I mentioned before, in this formula is only used for finding the electric field, the existence of the electric field. This is a test charge. Now here, this other formula, it looks different, right? And the Q here in this formula, I can't seem to see the cursor, there it is. The Q in this formula is not a test charge. That Q is actually the source charge. And so, to avoid confusion, I suggest you put a subscript of S whenever you want this formula, to use this formula. So what is this formula for? Well, this formula is if you want to calculate the electric field produced by a source charge. So if what you know is the magnitude of the source, the value of the source, that's enough so that you will be able to calculate the electric field at a certain distance r. So this formula involves, you can use this formula if you know the magnitude of the charge of the source. Okay, the units for electric field are newtons per coulomb or volts per meter. I hope you're not as confused, but you know, the way to really master these are two different formulas. E equals F over Q. Q here is the test charge, and this formula just is for a Q that is a test charge, but this E equals KQS over R squared. Q here is a source charge. Anyway, you will learn more about this if we solve more problems. First example, a test charge. So it's a test charge. Q equals 1 nanocoulomb is placed in a Cartesian plane with location 2 meters. The test charge experiences an electrostatic force of magnitude 10. What is the electric field strength at that location? So you got to remember, this problem it involves a test charge, and this test charge is placed at 2 meters, somewhere here. And so what is the purpose of putting a test charge there? Purpose is to figure out if there is an electric field in that point in space. So turns out that indeed there is an electric field at that point in space, because that test charge, according to the problem, experienced a force of 10 newtons. Just didn't say what direction, so I'll just assume that direction is this way. No, naka-experience yung force. The test charge experienced a force, therefore there must be an electric field. So the question is, what is the electric field strength at that location at 2,2? Well, you just use this formula. And why do we use this formula? Because what we are given is the test charge. 1 times 10 to the negative 9, because nano is negative 9. And force is 10 newtons. And the electric field is 10 times 10 to the 9. That's a really big electric field. Okay. At that point, how about this? A point charge Q is equal to 5 microcoulombs is fixed at the origin of a Cartesian plane Assume that there is no other charge in the universe. What is the electric field produced by this point's charge at point 1, 0? Okay, so clearly in this problem, this charge is the source charge. How do I know that? Because it says here the electric field produced by this point charge. So this point charge is producing electric field, and we are asked to calculate the electric field it produced at the point 1, 0. So let's call this 1 centimeter, 0 centimeter. At this point in space, here is our source charge. It's producing electric field at this point. So we calculate how much that is, the electric field that this source charge is produced at this point. We use this formula, K QS over R squared. And K is our 8.99 times 10 to the 9. QS is our source charge, 5 times 10 to the negative 6 coulombs. And so you have to remember the units of K, Newton meter squared per coulomb squared. And the distance of 1 centimeter, centi is times 10 to the negative 2. 1 times 10 to the negative 2 meters squared. I will not attempt to solve this, maybe padaya na lang mo. Oh, wait, let me approximate. It's probably around 45 times 10 to the 3, 10 to the 7. Probably around 4.5 times 10 to the 8. Alright. Yeah. Newtons per coulomb. Okay, so I hope you learned something today. Thank you.